The solar photosphere, typically a turbulent yet stable surface, begins to display an anomaly. A minuscule, yet impossibly dense object, a primordial black hole, breaches its fiery expanse. The star's internal equilibrium, maintained for billions of years, faces an unprecedented disruption. This is not a gradual process. It is an instantaneous, localized event with catastrophic implications. A primordial black hole, theorized remnants from the early universe, could be as small as an atom yet possess the mass of an asteroid. Its entry into the Sun's core would introduce an object with immense gravitational pull into a highly dynamic plasma-dominated environment. The scale difference is deceptive. Its mass is the critical factor. Upon entry, the black hole would not immediately consume the Sun in a dramatic flash. Instead, it would begin a slow, inexorable journey towards the stellar core. Its path would be dictated by the Sun's own immense gravity, pulling it inward, and the resistance of the superheated plasma it traverses. The journey itself would be a cascade of gravitational interactions. As the primordial black hole descends, its intense gravity generates powerful tidal forces within the Sun's plasma. These forces would rip apart atomic nuclei, creating friction and localized heating far beyond normal stellar processes. The internal structure, a delicate balance of gravity and pressure, would begin to experience unprecedented strain. The black hole would not simply bore a clean path. Instead, it would oscillate, shedding energy through gravitational waves and experiencing plasma drag. This dynamic interaction would create turbulent currents, disrupting the orderly flow of energy from the core outwards, slowly reconfiguring the Sun's internal hydrodynamics. Reaching the radiative zone, the black hole's presence would directly interfere with the transport of photons. Its immense mass would create a region where light could not easily escape, trapping energy and altering the thermal gradient. The efficiency of energy transfer within the Sun would diminish significantly, impacting its overall luminosity. Upon reaching the convective zone, the black hole would act as a powerful anchor, drawing in superheated plasma. This accretion would cause a localized increase in temperature and pressure, potentially triggering microflares deep within the Sun's interior. The surface would begin to show signs of this internal turmoil, though subtly at first. The black hole's journey to the core is a prolonged process. Taking potentially hundreds of thousands of years, it continuously consumes a minuscule amount of stellar material, growing imperceptibly larger while the Sun slowly loses mass from its interior. This is a battle of scales, with the star's immense size masking the intruder's destructive efficiency. Once anchored in the core, the black hole's accretion rate would increase. It would begin to consume the Sun's hydrogen and helium at an accelerating pace. This process would reduce the fuel available for fusion, paradoxically causing the fusion rate to initially increase in the surrounding layers as they collapse inward. The core, once a stable furnace, would become a gravitational drain. The black hole would continue to grow, carving out a void where nuclear fusion once powered the star. The Sun's energy generation would become increasingly inefficient, leading to observable changes across the electromagnetic spectrum. From an observational perspective, the Sun's luminosity would begin to fluctuate erratically. The stable energy output, a hallmark of its main sequence life, would be compromised by the internal chaos. Solar flares and coronal mass ejections would become more unpredictable and possibly more violent, driven by the intense gravitational perturbations within. The Sun's internal clock, governed by the slow consumption of hydrogen, would be thrown into disarray. The black hole acts as an accelerating agent of stellar decay, siphoning off mass that would otherwise fuel fusion. This accelerates the star's march towards its eventual demise, albeit through an entirely alien mechanism. The relentless consumption of core material by the black hole would lead to a gradual reduction in the Sun's overall mass. This mass loss, though initially imperceptible, would subtly alter the gravitational field permeating the solar system. Planetary orbits, currently stable, would slowly begin to expand outwards over vast timescales. The Sun's stellar classification would begin to shift. As the core fuel depletes and the star contracts around the black hole, its temperature and pressure gradients would change. It would no longer fit the stable parameters of a G2V dwarf star, slowly transitioning towards a state resembling a subgiant or even a red giant. But prematurely, the primary effect on the solar system would manifest as a continuous, albeit slow, change in the gravitational well of the Sun. Planets would spiral outward as the central mass diminishes, increasing orbital periods. The delicate orbital resonances that maintain planetary stability would gradually erode, introducing long-term instability. Unlike a star evolving naturally by burning fuel, this process involves a physical extraction of mass. It is akin to a slow-motion implosion, where the gravitational force of the black hole meticulously disassembles the star from its heart outward, rather than through nuclear exhaustion alone. Over hundreds of millions of years, the Sun would transform into a vastly different entity. Its fusion processes would dwindle, unable to compete with the central drain. It would become a cold, dark remnant, with a primordial black hole at its core, silently absorbing the last vestiges of a once vibrant star. As the black hole continuously siphons mass, the Sun's core eventually collapses inward upon itself, unable to sustain the outward pressure from fusion. The star contracts dramatically, its outer layers becoming increasingly tenuous and detached. This rapid contraction around the growing black hole signifies a critical phase transition, accelerating the star's structural decay. The Sun's once stable magnetic field, generated by its internal dynamo, would weaken and destabilize. The reduced convection and internal motion would diminish the field's strength, leading to a profound change in the solar wind and coronal activity. The protective heliosphere would gradually dissipate, exposing the solar system to interstellar radiation. With the cessation of significant fusion, the Sun's primary energy source vanishes. What little light and heat emanate would be residual, a fading echo of its former brilliance. The star transitions from an active furnace to a cooling ember, its luminosity plummeting over geological timescales. The stellar remnant grows darker and colder. What remains is not a white dwarf, but a dark, dense husk of a star, centered around the steadily growing black hole. This stellar corpse, devoid of internal nuclear processes, would be a gravitationally dominant, yet inert, mass. It would be a monument to a star's unexpected and violent end, an astronomical anomaly. The primordial black hole, now significantly more massive than its initial entry, would be the true heart of this stellar remnant. It would continue its slow accretion of the remaining stellar material, growing silently over eons. Its existence would redefine the nature of the star, transforming it into a dark celestial body with an invisible, destructive core. For the inner planets, the consequences would be catastrophic. Earth, stripped of solar warmth and light, would become a frozen, lifeless sphere. Its atmosphere, no longer protected by the heliosphere, would gradually erode into space. The delicate balance for life would be irrevocably broken, leaving a desolate landscape. The entire solar system would be plunged into an eternal night. The energy that once sustained life and dictated orbital mechanics would be gone, replaced by the silent, relentless pull of the central black hole. The planets would orbit a vacuum, a shadow of their former vibrant star, a cosmic graveyard. The Sun's identity as a G2-volt dwarf star, the anchor of our system, would be completely extinguished. It would no longer be a source of life or a beacon in the cosmos. Instead, it would stand as a chilling example of cosmic entropy, accelerated by the intrusion of an exotic primordial force, its very essence transformed. The Sun, once a vibrant yellow dwarf, would now exist as a cold, dense sphere, its remaining mass bound tightly by the central black hole. This inert celestial body, devoid of fusion, would emit only residual heat, a faint infrared glow lost in the vastness of space. It would be a stellar mausoleum, marking the Sun's ultimate transformation. The outer planets, Jupiter, Saturn, Uranus, and Neptune, though less immediately affected than Earth, would also experience profound changes. Their orbits would slowly widen, and their atmospheres, once bathed in solar wind and light, would cool dramatically. Their moons, once warmed by reflected sunlight, would plunge into perpetual sub-zero temperatures. The entire Kuiper belt and Oort cloud, the distant reservoirs of icy bodies, would become untethered from the Sun's gravitational influence over billions of years. Their tenuous bonds would weaken, allowing these comets and dwarf planets to slowly drift away into interstellar space, transforming the solar system into a less dense, darker void. The resulting system would be a unique cosmic entity, a primordial black hole encased within a dead star, orbited by frozen, wandering planets. It would differ from a standard neutron star or white dwarf remnant, representing a rare intersection of early universe physics and stellar evolution, a cosmic anomaly of profound scale. The black hole, having consumed the Sun, would persist for an unimaginable duration, far outlasting the universe's current age. Its Hawking radiation, the only means of its eventual evaporation, would take trillions upon trillions of years. This dark core would remain a silent monument to the Sun's demise, forever anchoring the remnant. This cosmic event serves as a stark reminder of the universe's inherent indifference to life's existence. The intricate dance of celestial mechanics, usually so predictable, can be abruptly and irrevocably altered by unforeseen, exotic phenomena, emphasizing the fragility of stellar equilibrium and the powerful forces at play. The timescale of this transformation, from initial intrusion to complete stellar collapse, would span millions of years. This slow, inexorable decay would be imperceptible to any single generation, yet observable through the lens of geological and astronomical time, a silent saga unfolding over vast cosmic ages. The solar system, once a cradle of life, would become a cold, dark monument orbiting an invisible point of immense gravity. The vibrant energy and light would be extinguished, leaving only the silent, icy ballet of planets around a cosmic void, a chilling testament to the universe's capacity for fundamental change. The fate of our Sun, as conceptualized by the intrusion of a primordial black hole, underscores the brutal impartiality of cosmic forces. From a radiant life-giver to a dark, cold husk, the transformation is a stark reminder that even the most stable celestial bodies are susceptible to the universe's unpredictable fundamental phenomena. Its light, once constant, is now an absence. This hypothetical scenario reveals the deep vulnerabilities within seemingly robust systems. The quiet void where a star once shone exemplifies the vast spectrum of destructive capabilities present in the cosmos, forces that operate on timescales and scales beyond human comprehension, making such events truly profound in their implications. Black holes, whether stellar mass or primordial, represent extreme densities where the laws of physics are pushed to their limits. Their gravitational influence, even from a minuscule form, can fundamentally re-engineer a star, demonstrating the enduring power and pervasive presence of these space-time distortions throughout the universe. The probability of a primordial black hole intersecting a star like the Sun is statistically low, yet not impossible. The universe is teeming with unknown variables, and such an event, however rare, serves as a thought experiment on cosmic hazards, a testament to the myriad ways stellar evolution can be catastrophically altered by exotic matter. The cosmos is not a static entity. It is a realm of constant creation and destruction, where stars are born, evolve, and ultimately meet their end through various mechanisms. The presence of a primordial black hole simply introduces an alternative, more abrupt pathway to stellar collapse, a silent and consuming internal force. In the grand cosmic ballet, every star, every galaxy, exists within a tapestry woven with known physical laws and unknown anomalies. The thought of an invisible, silent destroyer lurking within our own star forces a re-evaluation of celestial stability, urging a deeper understanding of the universe's most enigmatic constituents. Considering such a drastic fate for our central star, how does humanity's perception of cosmic security and our place within the universe fundamentally change, knowing that even our Sun could be silently consumed from within?